I am Dr. W. Gundule from Kamla Nehru Mahavidyalaya, Nagpur. Today we are going to discuss the next part of the coordination compound of chapter 9, and today we are discussing the valence bond theory of the complexes of coordination compound. And in this theory have important postulates, and this theory was given by the Pauling, and then by using the concept of hybridization we can explain the formation of complexes or the structure of complexes. And there are three types of complexes. One is octahedral geometry, then tetrahedral and square planar. Three types of geometry are there in case of complexes, and formation of complex of these three type of geometry, all this part we are discussing in today's presentation. So today's topic is the coordination compound, chapter number 9, and part 4 of this coordination compound. And as we know, today we are going to discuss the valence bond theory, that is in short VBT, which is given by Pauling. And here are the different topics have been given here: theories of bonding in complexes, valence bond theory. And as we know, there are different types of theories. In valence bond theory we are discussing the examples and formation of complex of octahedral, tetrahedral and square planar complexes. And here theories of bonding in complexes, and here metal ligand bondings in coordination compound take place or described by VBT and crystal field theory. And in addition to that also molecular orbital theory, ligand field theory and ACFT is also there. So these two main theories are here that we are going to discuss. And actually we know that Werner is the first, and Werner was the first to explain the bonding in coordination compound. But with the advancement of theories of valence and modern theories have been proposed to explain some characteristic properties of this compound, and therefore the color, geometry and magnetic properties. The main theories known as valence bond theory, crystal field theory, molecular orbital theory have been proposed. But we are discussing here today the valence bond theory in today's presentation. And this valence bond theory was proposed by Pauling, and important points are also there. So this valence bond theory consists of different steps, and these are given in the slide. The metal ion provide. The important points of this theory are given here. The first point is metal ion provide. These are the important postulates, important points of the valence bond theory given by the Pauling. And metal ion provides. Here some important points are there. Whenever in case of valence bond theory, as we know that complex contain metal ion and the ligand, and between the metal and ligand there is a formation of coordinate bond. So in complex coordinate bond is present, and that is why the complexes are also known as, or these compounds are known as coordination compound, because of the presence of formation of coordinate bond. And metal ion should have metal ion in the complex should have vacant d orbital, and which form the coordinate bond with the ligand. So here important point is that metal ion should have vacant orbital, ligand should have the lone pair of electron, one is a donor, other is acceptor. So here metal ion should have the vacant d orbital, and for the formation of coordinate bond with the ligand. So second point is that vacant d orbital along with the s and p orbital of the metal ions take part in the hybridization. So here we have to use the concept of hybridization for the formation of the complexes. Third point is that the number of vacant orbitals formed is equal to the number of ligand donor atoms surrounding to the metal ion, which equal to the coordination number of metals. So as we know, total number of ligand attached to the metal ion in the complex, it is the coordination number, or we can say that total number of coordinate bond present between metal and ligand is also known as the coordination number of that metal. So this is the third point. And overlapping between the vacant orbital of metal and the field orbital of ligands take place and forming the coordinate bond. Next point is that hybrid orbital used by metal ion point in the direction of the ligand, and therefore different geometries are there, and depending upon that, next point is given here. For this hybridization, n-1d orbital or nd orbital used in the hybridization and allow complexes to be form. And there are two types of complexes, whether we use n-1d orbital or nd orbital, means outer orbital, inner d orbital or outer d orbital. which d orbital we are using for the hybridization, and depending upon the type of d orbital, there are two types of complexes. One is outer orbital complex, inner orbital complex. Outer means when d orbital we are taking outer. When we take inner d orbital, then it is called inner orbital complexes. So two types of complexes are formed. And the last point is that for the hybridization, outer orbital complexes, nd orbitals are used for where, as in case of inner orbital complex, n minus 1d orbital are used. And the types of hybridization decide the structure of the complex. As we know, in case of types of hybridization, here mainly the three types of different types of hybridizations are here. And as we know, if the coordination number is 4, then the hybridization is sp3. When sp3 hybridization is there, geometry is the tetrahedral. Again now, coordination number is 4, but the hybridization is dsp2. In that case, the geometry is square planar. So when coordination number is 4, then the geometry are 2. Hybridizations are different, sp3, dsp2. sp3 tetrahedral, dsp2 square planar. In case of coordination number 6, then the hybridization is, there are two types of hybridization, d2sp3 or sp3d2, outer and inner. So sp3d2 outer d orbital, d2sp3 inner d orbital, and this is the octahedral geometry. So in case of sp3d2 or d2sp, so depending upon the types of hybridization, we decide the structure of the complex. So hybridizations mainly in the complexes are sp3, dsp2 and sp3d2 or d2sp3. And here some steps are shown here to understand the hybridization and metal ligand bonding. And here first of different steps are there to understand the metal ligand bonding. And here first step is the find the oxidation state of central metal line. What is the oxidation state of metal in the complex? So first of all, find out what is the oxidation state, like cobalt having 3 plus charge, nickel have 2 plus, copper have 2 plus. So what is the oxidation state of metal ion? First of all, we have to find out the oxidation state. Second is, then write the valence shell electronic configuration of metal ion. So after that, we have to write the valence shell electronic configuration of the particular metal ion. And after that, see whether the complex is low spin or high spin. So again we have to see low spin, whether this complex is low spin or high spin. As we know what is low spin, in case of low spin, number of unpaired electrons are less. In case of high spin, number of unpaired electrons are more. So whether it is low spin or high spin, also we have to find out. And number 4 point is that from the number of ligand, find the number of metal ion orbital required for the bonding. So from the number of ligand, how many ligands are there, and that much number of metal ion orbitals are required for the bonding. So if the ligands are 4, we require the 4 metal orbital for the bonding. So depending upon the number of ligand, so orbital of metal ions are required. And number 5 is identify the orbitals of metal ion available for hybridization and type of hybridization involved. So after identifying the orbitals of metal ion, how many orbitals of metal ions available for the hybridization, and depending upon that, the hybridization is involved. And after that, write electronic configuration of after the hybridization also. And after hybridization also you have to write the electronic configuration. And next point is that show the filling of orbital after complex formation. As we know, complex orbital also filled in the similar way as atomic orbitals. So here we are also taking some examples how the filling of orbitals are take place. And after that, determine number of unpaired electron and predict magnetic behavior at the complex. So how many unpaired electrons are there? If the complex have 2 or more unpaired electron, or they have an unpaired electron, in that case the magnetic behavior that complex of that substance is a paramagnetic. When all the electrons are paired in the complex, then that complex is a diamagnetic. So magnetic behavior we can be decided on the basis of this, how many number of unpaired electrons are present, or whether having no unpaired electron. So depending upon the unpaired electron present or all the electrons are paired, magnetic behaviors can be decided. So complexes are generally paramagnetic, or complexes may be diamagnetic. So these are the different steps to understand the metal ligand bonding in the complex. Now we are taking some examples of 3 types of geometry. One is octahedral geometry, second is tetrahedral, and then square planar geometry. So in case of octahedral, 2 examples of complexes we have taken here. And first example is the hexaamine cobalt 3 complex. So here that is CONH36 3 plus. So this is the example of complex, and in this complex now See the formation of the complex. 3 steps are there. This is the oxidation state of the cobalt 3. 3 is the oxidation state, and we know in this complex cobalt is the metal ion and amine is the ligand. So here this cobalt have atomic number 27, and therefore outer valential electron configuration is argon 3d7 4s2. So 3 oxidation state is there. So cobalt have valential configuration is 3d7 4s2. So 2 electron loss from 4s and 1 from the d orbital. So after loss of 3 electron, cobalt have 3 oxidation state. So 6 electrons are left. So here configuration is 3d7 4s2. So 2 electron from 4s and 1 from this 3d. So 3 electron lost, and remaining electrons are here. These are the 5 and the 6 total electrons are there in a 3d orbital. So 3d orbitals have 3 electrons. Here 3d orbitals have these 6 electrons, and now after this, and this is the octahedral complex, and the 6 ligands are there, and therefore we require 6 metal orbital vacant. So here 1 2 3 4 orbitals are vacant, but now we require again 2 orbitals of 3d. We require total 6 d orbital. So here 3 and 1 4. So these 2 orbital we have to make vacant, and for this case ये दोनों इलेक्ट्रॉन को इधर शिफ्ट कर सकते हैं, because here is a space, here is single electrons. So these 2 electron in the excited state, we have to these 2 electrons shifted here, and when they are shifted they get paired in this way. So this total 6 electrons occupy in a 3 orbitals, 2 electron in 1 orbital in this way. So in this way, after shifting these 2 electron here shown here, these 2 d orbital made vacant. Now in the excited state 1 2 3 4 5 6 6 इलेक्ट्रॉन इसमें 6 ऑर्बिटल्स आर वैकेंट नाउ, 6 ऑर्बिटल्स आर वैकेंट, एंड आफ्टर दिस नाउ इस तो इसमें ये जो है 2 इसमें से d ऑर्बिटल वैकेंट बनाना है. 2 इलेक्ट्रॉन को इधर शिफ्ट कर दिया है, तो 2 d ऑर्बिटल अभी वैकेंट हो गए, और एक्साइटेड स्टेट में टोटल 6 इलेक्ट्रॉन वैकेंट हो गए हैं. तो ये 6 इलेक्ट्रॉन जो है, तो इसमें से 2 d ऑर्बिटल, 1 s ऑर्बिटल एंड 3 p ऑर्बिटल अंडरगो हाइब्रिडाइजेशन एंड फॉर्मिंग न्यू 6 sp d2 sp3 हाइब्रिड ऑर्बिटल. तो इसमें क्या करना है कि ये 2 d ऑर्बिटल, 2 d ऑर्बिटल, 1 s and 3 p ऑर्बिटल अंडरगो हाइब्रिडाइजेशन एंड फॉर्मिंग 6 d2 sp3 hybrid orbital of equivalent energy and shape. What is d2 sp3? d2 sp3 means 2 d orbital, 1 s and 3 p. So d2 sp3 hybridization, we can say that in this hybridization 2 d orbital, 1 s and 3 p orbital undergo hybridization forming 6 d2 sp3 hybrid orbital of equivalent energy and shape. So in this way, these 6 orbital forming, these are the 6 hybrid orbital, and these hybrid orbital now here forming the 6 ligands are there. So these 6 ligands, 1 2 3 4 5 6 ligands are there. They donate electron pair to the vacant orbital of metal. So in this way, vacant hybrid orbitals are vacant, and 6 ligand donate electron pair. So this is in a red color shown here, pink color. So what is now 2 electron, these are the electron pair donated from the ligand. 1 2 3 4 5 6 ammonia are there. They donate 6 electron pair. इस टाइप से ये इलेक्ट्रॉन डोनेट करने के बाद ये वैकेंट 6 ऑर्बिटल्स है, 6 वैकेंट ऑर्बिटल ऑफ मेटल, ये एक्सेप्ट करते हैं अमोनिया से एक इलेक्ट्रॉन पेयर एंड फॉर्मिंग दिस टाइप ऑफ कॉम्प्लेक्स. सो देयर आर 6 कोऑर्डिनेशन नंबर. So coordination number 6 and total 6 coordinate bonds are present in the complex. So the hybridization is d2 sp3 and shape of the complex is the shown here. तो ये shape है, cobalt is a central metal ion and 6 ligands are surrounded to this and having a 3+ charge. So this is the structure, and this structure is the octahedral structure of the complex. So this is the formation of hexamine cobalt 3 complex, 3+ complex. So these are the steps. So this is the valential configuration, this is the excited state configuration, this is hybridization state of configuration, and this is the formation of complex of hexamine cobalt 3+ complex structure, and this is the geometry of the complex. So in this complex, cobalt is metal, ammonia is the ligand, and this is the 6 ammonia are there, and hybridization is d2 sp3 and geometry is octahedral. So in this way we can explain the formation of octahedral complex. And another complex is also there. We can also write in this way, octahedral complex, and complex is a COF6 3-. So in case of first complex, ammonia was the neutral ligand. In this case, this is the negatively charged ligand. Fluorine is F-, so negatively charged ligand. So 6 ligands are there. Again, coordination number is 6. So the formation of complex can be shown here step by step. So in this complex of cobalt F6 3-, cobalt is again the central metal ion. इसमें कोबाल्ट क्या है, सेंट्रल मेटल आयन है, और ये फ्लोरीन कितने 6, कोऑर्डिनेशन नंबर कितना है 6, एंड नाउ कोबाल्ट हैव अगेन नाउ हियर ये फ्लोरीन का 6-, राइट साइड में आएंगे तो +6 एंड कोबाल्ट, सो व्हाट इज हियर वी कैन -3, तो 6 में से -3 गए तो कितना आता है 3+. एज वी नो हाउ टू फाइंड द ऑक्सीडेशन स्टेट ऑफ कोबाल्ट, वो तो अपन ने देखा है कि चार्ज ऑन द मेटल प्लस चार्ज ऑन द लिगैंड इज इक्वल टू चार्ज ऑन द कॉम्प्लेक्स है, तो ये इस टाइप से निकाल सकते हैं. कोबाल्ट F6 3-, तो कोबाल्ट का ऑक्सीडेशन स्टेट या चार्ज कितना है उसमें 3+ चार्ज है. तो कैसे निकालते हैं, कोबाल्ट का निकालना है तो उसका x करना है, फ्लोरीन का -1 है, टोटल 6 है, तो -6 इक्वल टू -3 चार्ज ऑन द कॉम्प्लेक्स. तो ये -6 है तो ये राइट साइड में आएंगे तो +6 और ये -3 +3, तो x की वैल्यू आ जाएगी कोबाल्ट की -+3. तो कोबाल्ट है +3 ऑक्सीडेशन स्टेट. सो हियर इज शोन atomic orbitals of cobalt is in a +3 और ऑक्सीडेशन स्टेट कितना उसका 3. तो अगेन सेम द कॉन्फ़िगरेशन, दिस इज द वैलेंशियल कॉन्फ़िगरेशन ऑफ कोबाल्ट. तो ये 3d 4s 4p 4d, and in this case now here we take the, here this is the first complex, octahedral complex we have seen, and that was the D2sp3 means inner orbital complex. Now here these are the configuration of cobalt 3. तो ग्राउंड स्टेट वैलेंस शेल में उसके हैं तीन चार्ज है, तो 3 इलेक्ट्रॉन चले जाएंगे. 2 उसका कॉन्फ़िगरेशन है 3d7 4s2, तो 4s में से 2 गए, 2 गए इलेक्ट्रॉन्स और यहाँ से 1 इलेक्ट्रॉन गया, तो इसमें बचे 6 इलेक्ट्रॉन्स. तो वैलेंस शेल 3d ऑर्बिटल नाउ 6 इलेक्ट्रॉन. सो नाउ हियर 1 2 3 4 unpaired electrons are there, and actually we require the 6th orbital vacant. So instead of this in this case we are using 1s orbital, 3p orbital and 4d orbital 2 here vacant. So here we have used this. So in this case we are not disturbing this 3d orbital, and we are using for the hybridization, and hybridization is sp3d2. तो d ऑर्बिटल इज आउटर, इसमें d ऑर्बिटल आउटर का दिया है, तो ये आउटर ऑर्बिटल कॉम्प्लेक्स है. तो इसमें ये 1s 3p and 2d orbital undergo hybridization forming 6 sp3d2 hybrid orbital of equivalent energy and shape. तो इसमें d ऑर्बिटल आउटर ऑर्बिटल यूज किया है. तो दिस इज द हाइब्रिडाइज्ड ऑर्बिटल्स ऑफ कोबाल्ट 3 आयन, एंड हाइब्रिडाइजेशन इज sp3d2. तो ये देखो इस टाइप से sp3d2 d ऑर्बिटल वी यूज हियर, आउटर ऑर्बिटल यूज किया है, इसलिए ये आउटर ऑर्बिटल कॉम्प्लेक्स है. ये कॉन्फ़िगरेशन वैसा ही है, और इसमें जो फिर ये जो लिगेंड्स है 6, तो डोनेट इलेक्ट्रॉन पेयर 1 इलेक्ट्रॉन पेयर, सेकंड, थर्ड, 4, 5, 6, तो 6 इलेक्ट्रॉन पेयर डोनेट करेंगे, और मेटल के बाद 6 ऑर्बिटल वैकेंट है. इट एक्सेप्ट इलेक्ट्रॉन पेयर. इन दिस केस लिगेंड इज डोनर, मेटल इज एक्सेप्टर, एंड देयरफॉर फॉर्मिंग दिस coordinate bond 1 2 3 4 5 6 coordinate bond. So coordinate number is 6, ligands are 6. So hybridization is sp3d2. So sp3d2. In case of octahedral, 2 types of complexes are there: inner orbital complex, outer orbital octahedral complex. So first complex that we have seen, cobalt 3 plus is the inner orbital complex, because we use inner orbital of d, and in this case we use the outer d orbital, therefore it is outer orbital complex. So this is the another example of octahedral complex, and that is hexafluorocobalt 3 plus complex. So in this case the metal is cobalt, ligand is fluoride, and in case of metal cobalt have 3 plus charge, and the hybridization is sp3d2. It is outer orbital complex, and this is the having the octahedral complex and outer orbital complex, and hybridization is sp3d2. So this is the formation of complex. तो ये पहले इलेक्ट्रॉनिक कॉन्फ़िगरेशन लिखना है मेटल का, उसके बाद में वैकेंट ऑर्बिटल बनाना है, हाइब्रिडाइजेशन, उसके बाद में लिगेंड डोनेट करते हैं इलेक्ट्रॉन पेयर, एंड फॉर्मिंग दिस टाइप ऑफ complexes. So we have seen two examples of octahedral, inner orbital and outer orbital complexes. Depending upon the n-1 d orbital we are using, or we are using n-d orbital. So there are inner and outer orbital. One thing is again here that in this case, this is the formational complex, this is the formational complex, and in this complex 1, 2, 3, 4, 4 unpaired electrons. So it is the high spin complex. Number of unpaired electrons are more, though. So this is the high spin complexes. And in case of the hexamin cobalt 3 plus complex, unpaired electron was 0. That means it is, that one is the low spin complex. So again now we have seen low spin and high spin. So this complex is a high spin complex because of the presence of 4 unpaired electrons. And the first complex that we have seen, inner orbital complex, is a low spin complex. So these are the two examples of octahedral complex. Now next is the tetrahedral complex. In case of tetrahedral complex, coordination number is 4 and hybridization is sp3. Tetrahedral means sp3 hybridization. So here example is taken is a nickel tetrachloronickel 2. So nickel have 2 plus charge, and in this case as we know, nickel having the atom number 28 and configuration is 3d8 4s2. So what is 3d8 4s2 here? 3d8 shown here 6, 7, 8. 3d8 4s2. Now nickel, in this complex nickel have 2 plus charge. So 2 electron loss from 4s, and now these are the 8 electrons left. So this is the configuration of nickel 2 plus. And number here, after that what is now, we require 4 orbital vacant, and now in this case all the 1 4s and 3 4p orbitals are already vacant, and therefore 1 4s and 3p orbital undergo hybridization, forming 4 sp3 hybrid orbital of equivalent energy and shape. So there is no any excited state. So in formation of tetrahedral complex, so 1 4s and 3p orbitals are already vacant, and therefore they undergo sp3 hybridization. So 1s and 3p orbital undergo hybridization, forming sp3 hybrid orbital of equivalent energy and shape. Now 4 ligands are there, 4 Cl, 1, 2, 3, 4. So they donate electron pair to the vacant orbital of metal and forming these coordinate bonds. So 1, 2, 3, 4 are the 4 coordinate bonds. 4 electrons accepted by the vacant orbital of metal, and 4 ligands donate the electron pair, and these are the electron pair donated from the ligand, and 1, 2, 3, 4 are the coordinate bond. And hybridization is sp3. इसमें देखो s orbital is 1 and p orbitals are 3, 1, 2, 3. तो ऐसे ये 1 और ये टोटल 4 sp3. इसमें दिखा ये है s 1 ही है, p 3 है, तो sp3 ऐसा ये hybridization है sp3. Whenever there is a sp3 hybridization, the shape is the tetrahedral shape. So in this way, geometry of the tetrahedral is shown. 4 corners are there in tetrahedral, 1, 2, 3, 4, and this is the geometry of the complex of this tetrahedral, and coordination number in this case is 4. So in this way, 4 ligands are there, coordination number is 4, and this is the tetrahedral geometry shown for this complex. So nickel Cl4 2 minus form this type of tetrahedral complex, and these are the steps 1, 2 and 3 are the steps. There is no any excited state. Rearrangement is not required because already 4 orbitals are vacant in this metal orbital, and after that they donate electron pair forming this type of complex. So this is another example, that is tetrahedral complex. And now in case of coordination number 4, sp3 hybridization having the tetrahedral complex and geometry. And now in case of coordination number 4, another geometry is there which is known as square planar complex. Coordination number 4 also here in square planar complex. In case of square planar complex, the hybridization is dsp2. So here this is the dsp2 is shown here. This is the dsp2 hybridization. So again now here complex is a nickel Cn4 2 minus. So in case of ligand also 4, ligands are 4 means coordination number is 4. And in this way nickel 2 plus is also in this complex, nickel is in a +2 state. तो निकल का कॉन्फ़िगरेशन ग्राउंड स्टेट में क्या होता है कि 3d8 4s2. तो 3d8 electrons are already here. 4s now having 2 electrons, that 2 electron is lost, and this is the configuration of nickel 2 plus. और निकल का कॉन्फ़िगरेशन क्या होता था 3d7 4s2, बट निकल 2 का है 3d8 4s0. So this is the 2 electron loss from the 4s. and these are the 8 electrons in the 3D orbital. And now what is now here hybridization is dsp2 in case of square planar. So we require one d orbital vacant in this case. So there is a excited state of nickel 2, and in case of nickel 2 excited state, one orbital made vacant. So see, one electron of this is shifted here. Here is just यहाँ पे जगह है, ये यहाँ पे सिंगल इलेक्ट्रॉन है, तो इस इलेक्ट्रॉन को यहाँ पे शिफ्ट करो, ये ऐसा अपोजिटली स्पीड उसका स्पीड रहेगा, तो सभी में पेयर्ड इलेक्ट्रॉन हो गए इसको शिफ्ट करने के बाद, और वन डी ऑर्बिटल मेड वैकेंट. तो हियर वन डी ऑर्बिटल, one s orbital and 3p orbital undergo hybridization and forming dsp2 hybrid orbital of equal energy and shape. So 1, 2, 3, 4. So here dsp2, out of here 1s, 1d, 1s and 2p. So this is the dsp2 hybridization of the nickel 2. Now this vacant orbital accept electron pair from the 4 ligand CN cyano group. Cyanides are there 1, 2, 3, 4. So these are the dots means electron pair. So 4 electron pair taken from the 4 ligand and forming this type of complex NiCN4 2 minus. So in this case a nickel have 2 plus charge, CN the 4 ligands are 4 and 2 minus, so complex of 2 minus charge. So in this way 4 pairs of electrons from the cyanide ligand groups are donated and forming this type of complex tetracyanonickel 2 complex. In this is the another square planar complex. So tetrahedral, and in case of square planar coordination number is 4, but the hybridizations are sp3, then tetrahedral, hybridization is dsp2, then square planar complexes. So today we have discussed the formation structure of complexes on the basis of valence bond theory, and here we have taken the example of octahedral, tetrahedral and square planar. In case of octahedral, we have already discussed outer orbital complex and inner orbital complex depending upon the use of d orbital, and also in case of coordination number 4, whether the complex is sp3 or dsp2 means tetrahedral or square planar. So these are the 4 examples of the formation of complex we have explained on the basis of valence bond theory. So here by using valence bond theory, structure of the complex can be decided, and as we know there are a number of theories to explain the formation of complex, that is valence bond theory, molecular orbital theory and also crystal field theory. So in the next part we are going to discuss the crystal field theory of the formation of complexes. So this is also very important and modern theory, that in short it is known as the CFT. So CFT we are discussing in the next part of this chapter, and that was the last part. That is the last part, and here today we have discussed the valence bond theory, and that is CFT and their important points, and for the formation of octahedral complex, splitting of d orbital in octahedral complex, and also tetrahedral complex and square planar complex also is there. All the 3 geometry in case of CFT is also there, and explain the formation of complexes, and that theory is more that is explaining clearly and also give evidences for the formation of structure of the complexes as compared to valence bond theory, because valence bond theory has certain limitation. So what are the limitations and what are, how the CFT theory explain the structure, all this part we will discuss in the next part. So today we have discussed some examples and formation of what is the valence bond theory of the complexes or coordination compounds.